1989 E1. And this is looks like a sphere of radius r that has minus q spread throughout the volume, and then it has a positive point charge at the center. So this really looks like a model of the atom, a very simple model of the atom, but still, this is how I'm going to view this. And we're going to determine each of the following things based on, we got a point charge here, and then we have this minus q that's spread throughout the volume, and they're very nice to us in making it uniformly distributed. Oh, also, that picture has nothing to do with number 1. That actually belongs on the next page for number 2. All right, part A, the electric field outside the sphere at a distance r greater than r. Okay, so outside the sphere, so out here at a distance r. So let's start with Gauss's law, because we have nice spherical symmetry here. So let's use that spherical symmetry to our advantage. And that means that the Q enclosed is going to be the plus Q at the center, and then we've now enclosed all of the minus Q from the volume there, and that will mean that the total enclosed charge is 0, and the result is that the electric field is also 0. Part B, the electric potential. We can do the same sort of idea for electric potential, because we can do electric potential from a point charge is kq enclosed over r. And again, the q enclosed is going to be 0. So the electric potential outside the sphere is also going to be 0. What we have here is essentially a neutral atom. All right, now the electric field inside that sphere. Now the electric field inside that sphere vaguely sphere. Okay, now R. Notice that we have now enclosed part of the negative and all of the positive. So starting with Gauss's law again, our Q enclosed is going to be like one of those previous problems where we had a positive charge at the center and then we had part of the negative charge enclosed. So for the negative charge, Q enclosed over 4/3 pi r cubed equals the negative q over 4/3 pi total radius, and the constants are going to cancel. So for the negative, how much of the negative charge have we enclosed? It will be the ratio of the cube of the radii. Now, that's not all of the charge, because we have this plus charge here at the center. So Q enclosed actually is going to be the plus charge at the center, and then the ratio of the negative charge and ratio of the r cubed here. So this is just the negative Q calculation, because now we have to add in the plus charge, add in plus Q from center. Also, the area, we have a spherical symmetry here, is going to be 4 pi little r squared. And we're going to take these guys and plug them into Gauss's law. And I need space. Where am I going to put this? Here, I'll switch to blue, put a bar here, and this will be C continued. So we're going to have Q minus Q r cubed over r cubed all over epsilon naught equals E 4 pi r squared. And when we divide this guy over, factor out a Q, we're going to have Q over epsilon naught. Oh, and the 4 pi, don't forget the 4 pi. Okay, so I've taken care of that and that, and that, and that. And then I'm going to have 1 minus r cubed over r cubed and then a 1 over r squared. That still looks awkward. We can clean it up a little bit. Q over 4 pi epsilon naught. And then we'll have 1 over r squared minus r over r cubed. All right. Now, if you think about this, what this part is saying is we are outside the positive charge, so we're undergoing the 1 over r squared relationship, but we're still inside the negative charge, so we're gradually increasing the electric field from that one, and eventually we will have enclosed all of this, and this will also become a 1 over r squared like that guy is, and we'll be back to the situation that we have in part A, where we've enclosed all of both charges. The total enclosed charge is 0, and the electric field will be 0. So our answer from C is going to turn into our answer from A once we get to little r is equal to big R. All right, I'm going to have to clear this stuff out so that I can look at part D, but I don't want to clear it all out because I think I'm going to have to use this answer here as part of my work for part D. Part D, the electric potential inside the sphere at that distance. Okay, now to get the electric potential inside the sphere, we're going to have to play the game that we played in class as we were discussing this. We're going to have to go for a very far distance away, walk to the surface of the sphere, and then once we've gotten to the surface of the sphere, we're going to have to go into the sphere. All right, because again, the potential is more like climbing a mountain. We are the travelers climbing the mountain, and this mountain is there whether or not we climb the mountain. So we have to look at the relationship between electric field and voltage. So the change in voltage is going to be the result of moving through the electric field. Now, this electric field changes depending on where we are. So from infinity, from very far away to big R, we have one setup, and then from big R to little r, we have a different setup. So this integral is going to look like this. We're going to have from very far away to the surface, E dot dr, and then we're going to go from the surface inside, also E dot dr. But we're going to have to deal with E out and E in. And then this is going to get us the whole thing from that's not negative sign, from very far away to somewhere inside the sphere. All right, now, having done that, what's the electric field outside the sphere? Well, we already did that. That was part A. That puppy, very kindly, is 0. For the inside, we have this ugly expression that we're going to have to integrate. So for the inside, we're going to have minus integral q over 4 pi epsilon naught, parentheses, not another integral, parentheses 1 over r squared minus r over a constant cubed dr, and we're going to go from big R to little r. All right, and this guy, this is, that's an equal sign, and then the minus sign that's part of the equation. And this is just going to be V of R, because V at very far away is 0, because the electric field at very far away is 0. So this is just going to be V of R. And actually, no, I take that back. That's going to be V of R minus V of surface. Now this guy is, it's going to be 0, so we're going to end up with this guy, but we need to keep in mind that we're moving from the surface, in this case, to inside, because that's our limits on the right side of the equation here. So we're going to have minus q over 4 pi epsilon naught minus 1 over r, because this is the same thing as saying r to the minus 2, and then we're going to add 1 to this exponent. It'll become minus 1, and then we divide by our new exponent, which is a minus 1. So Here's our 1 over r, it's the same as r to the minus 1, and then dividing by that produces that minus sign. Meanwhile, over here we have minus r squared over 2r cubed. And we're going to go from big R to little r. All right, now cleaning this up a little bit, meaning putting in the little r, putting in the big R, and then distributing that minus sign, which we could just distribute the minus sign like this. And then we have little r minus big R. We're going to get v of r, because again, remember at the surface, that guy's going to be 0. We have q over 4 pi epsilon naught. And then the quantities 1 over r plus r squared over 2r cubed minus, and when we plug in the big R there, we're going to have 1 over big R plus big R squared over 2 big R cubed. And all of that's the lower limit, so there's a great big fat minus sign out front of it. That's this minus sign, same minus sign. And r squared over r cubed kills those guys, and we have 1 over r plus 1 over 2r. So that's 2 over 2r. That gets us 3 over 2r. So minus 3 over 2r. Here's our essentially a constant for dealing with the fact that we're going to be stepping inside a sphere. All right, and that gets us our voltage inside the sphere as a function of how far am I from the center of the sphere.